Welcome back, folks. On lesson 2.2, we're talking about the power rule. The objective is to find derivatives by applying the power rule. Now, in 2.1, I showed you the definition of derivatives involving limits and looked at calculating derivatives using that limit definition. Now, we can find the derivative of any function using that definition. Problem is it's kind of a pain in the butt to use. That's why we're going to want some different rules, some different derivative formulas. Okay, the power rule is going to be the first one we start off with here. All right, so here is our power rule. Let's say that if f of x is equal to x to the n, okay, where n is any power here, so we could be talking like x squared, x to the 7, x to the 42, or even fractions or negative numbers. We'll get into that later. Okay, so if f of x is equal to x to the n, then f prime of x, the derivative of x, is equal to n times x minus 1. Okay, so for example, let's say that our f of x is equal to just x squared, something simple. That means that the derivative of x is going to be equal to, well, in this case, our n is just a 2. We'll put that n out front. X to the n minus 1, 2 minus 1 is 1, so that'll just be 2x to the 1, or in other words, just 2x. All right, simple formula to use. Now, another way we could express that is using this kind of derivative operator. Again, if our function we're talking about, or our expression to the n, the derivative of x to the n is just n times x to the n minus 1. Same formula, just kind of two different ways to talk about that. All right, now where is that formula coming from? Well, let's prove it for you here quick. Again, this will be kind of an informal proof. We're not going to spend a half an hour hitting all the details. We'll just do enough to convince you that that power rule is true, that it works. Okay, if I want to take the derivative with respect to x of x to the n, okay, where n again could be any exponent, we're going to define that as the limit as h goes to 0 of x plus h to the n minus x to the n over h. Okay, now I can't evaluate this directly because I have this h on the bottom. So what we do is we'd expand the top, and in the case of an x squared, we'd FOIL these together, x plus h times x plus h. If it was a third, we'd multiply by another x plus h. If it was some higher power, we'd have to FOIL a whole bunch of times. But anyways, when we do that, we're always going to end up with an x to the n term, which is going to cancel with that final minus x to the n that comes from here. We're always going to have a term that is n times x to the n minus 1 times an h, plus a whole bunch of other terms depending on how many or what power our n is. We're not going to worry about what the specific coefficients are, but we know they'll have h's in them. So what I could do then is I could factor an h out of all these remaining terms. I'll have an h on top, h on bottom then. We can cancel those. So now the h on the bottom is removed. Now we don't have to worry about division by 0. We can just substitute the 0 in for all the h's. Now this first term without the h, nothing's going to happen there when we send h to 0. The rest of these terms with the other h's will cancel out. And we're left with then, what survives is just that n times x to the n minus 1, okay, what we get from the power rule. All right, again, not a formal proof, but hopefully after looking through that, you're convinced that, yep, that power rule is true. Let's go ahead and look at applying that power rule to some different functions here. Okay, so use the power rule to evaluate each derivative. Okay, if f of x equals x squared, we want to find f prime of x, the derivative of f of. We already did that one. F prime of x will just be equal to, our n is a 2, so rule says put the 2 out front, subtract 1, and we can just say 2x. Technically we could put a 1 here, but usually you don't include that. All right, b, same idea. If g of x equals x to the 5th, we want to find g prime of x. Well, g prime of x will just be equal to, the n is 5, so we'll have a 5 out front, x to the 5 minus 1, that'd be a 4. All right, so again, there's my derivative function. All right, C, we want if h of x equals x to the 4th. Here we want to find h prime of 3. So the value of the derivative when x is equal to 3. So really a two-step problem. First thing is going to be to find h prime of x. Okay, my n is 4, so it'll just be a 4x to the 4 minus 1 is 3. And then once I have that formula for my derivative, we can plug the 3 in. So h prime of 3 is going to be equal to 4 times 3 to the 3rd. Okay, I'd recommend do this in two steps. Find the rule first, then evaluate. Okay, don't try to do both at the same time. And that's going to be a 4 times 3 to the 3rd is 27. So 108 would be the rate of change of h of x at x equals 3, the slope of that tangent line. Okay, the value of the derivative at x equals 3. All right, that's the basics of the power rule. Why don't you take a minute, pause the video, give D, E, and F a shot, and then hit play to check your work. So the power rule works for simple monomials, okay, x to whole number powers. What we're going to see in this next example is that it also works for certain simple rational functions, okay, functions with fractions, and radical functions, functions with roots. Let's take a look at that. Again, use the power rule to evaluate each derivative. So if y equals 1 over x squared, we want to find dy over dx, the derivative of y with respect to x. Okay, and the trick with this is I want to take this 1 over x squared and rewrite it in terms of an exponent. Okay, we can call this y equals x to the negative 2 power. Okay, because remember rules of exponents, if I have a base raised to a negative n power, that's going to be the same thing as 1 over b to the n. Okay, those negative exponents just say to flip to the bottom side of the fraction. And once I have that, I can find my dy over dx, or I could just say y prime is equal to, we'll put the n, which is negative 2 out front, times x to the, well, n minus 1, negative 2 minus 1 is going to be a negative 3. All right, there's my derivative, but we'll usually write that without negative exponents. We'll call that a negative 2 on top over x to the 3rd. All right, so there's my y prime in this case here. All right, kind of same idea with b. If y equals 3rd root x is our function, we want to find derivative of y with respect to x. My first step is going to be rewriting y in terms of just x raised to a power. And for this one, I'm going to use is my rational exponents. Okay, rule for that is if we have the, let's say, nth root of x to the m power, that's equal to, in terms of exponents, x to the m divided by n power. All right, where my denominator is the index of the radical, the type of root we're looking at, and my numerator is any power we're raised to. Now in this case, I've got a 3rd root. We can think of this as an x to the 1. So I could say this is x to the 1/3 power. And once I've rewritten it in terms of exponents, now I'm ready to find the derivative. We can say this is y prime's equal to 1/3 times x to the 1/3 minus 1. So to get from here to here, subtracting 1, okay, in other words, subtracting 3 over 3, we'd have a negative 2/3 power, which we can rewrite in terms of positive exponents as 1 over 3 3rd root still x squared. All right, last one then kind of combines what we did in the first two problems here, and then also we're going to evaluate our derivative at x equals 3. So if y equals 1 over square root x to the third, we want to find the derivative of y with respect to x evaluated at x equals 4. Okay, this is kind of the same thing as, let's say, f prime of 4. Okay, find the derivative at 4. Now, since there's no f here, we're just using the y. This would be the kind of best notation for that. First step, let's rewrite this equation in terms of exponents. So I can say y is equal to x to the negative, because we're on the bottom part of the fraction. As far as rational exponents go, we'll do a 3 on top, because that's the power my x is being raised to, over square root, so it's not written here, but it's implied that that index is 2. All right, now I can find the derivative, the y prime, which would be equal to, put the n out front, negative 3/2 times x to the, if I take away 1 from here to here, in other words, minus 2 over 2, that'd be x to the negative 5/2. All right, which we can rewrite with positive exponents as a negative 3 over 2. And on the bottom, we'd have a square root still. That's the type of root we're dealing with, x to the 5th. All right, so there's our derivative equation. And then once I have that, now I can evaluate it for x equals 4. Now with this y prime notation, there's not a great way to show us plugging 4 in, which is why I am going to use the dy over dx evaluated x equals 4 notation, just to kind of show what we're doing with that derivative of y. Well, that's just going to be equal to negative 3 over 2 times the square root of 4 to the 5th. And I'm going to make that 4 to the 5th look a little less like 45 here quick. There we go. All right, and I'm just going to do my calculator in this part. I don't really feel like finding 4 to the 5th off the top of my head. That's going to be a negative 3 over 2 times square root of negative 4 of 4 to the 5th would just be a 64. All right, D, E, and F are similar. I want you once again take a minute, pause the video, work through these, and then again hit play to check your answer before you move on. Next thing we're going to look at are some basic derivative rules. And these aren't going to just apply when we're using the power rule. They're going to apply to all derivatives in general. And where each of these are coming from are just really coming from rules of limits. Remember, a derivative is essentially just taking a limit. We know that we can do some things with constants of limits, constants times limits, and addition or subtraction of limits. Okay, that's why all these rules apply. First one, constant rule, derivative of a constant such as a 7 is just a 0. Constant multiple rule, this says that if we're taking the derivative of a constant times a function, we can pull that constant out and then just worry about finding the derivative of that function individually. And last one, the sum/difference rule, says that if I'm taking the derivative of two functions added together or subtracted, I can find those derivatives separately and then just add, there should be a subtraction symbol there as well for the plus minus, add or subtract those derivatives by themselves. So let's go ahead and utilize those rules. Problem 3 says evaluate each derivative. And what those rules are going to do is allow us to find derivatives of more complicated functions, which are essentially just multiple functions we can think of them as put together here. All right, So here we have d over dx of what's in parentheses. Okay, again, you can think of that as an operator. Take the derivative of whatever's in parentheses here. And we can do that a part at a time. First part, we have 2 times x to the third. All right, well, I'm going to take that constant here and just write 2 times. And we'll figure out what x to the third here is in a second. Using our power rule, x to the third is going to be a 3 times x squared. In this case, our n is 3, so we'll pull that out front. And then just go 3 minus 1 to get the 2. Now, we can obviously combine these right off the bat, but just for your note's sake, we'll do a little more work than we need to. Okay, and then minus, we can think of this minus 10x as 10 to the 1. So we have that 10 as a constant. And then we'll say times 1x to the 0. Obviously, I don't need this times 1. And x to the 0 is just the 1. We'll clean that up in a second. And then plus the 5. Now, we can think of that as just a 5 times, we could say, x to the 0th power. Well, when I multiply that by 0, x to the negative 1, I suppose, that's just going to cancel out. And that's just utilizing our constant rule. We know that the derivative of a constant is always just 0, like we said before. Okay, then so for a final answer, we'd end up with 2 times 3 is 6, so 6x squared minus 10. Again, x to the 1 is just 1. Okay, so there's the derivative of that expression. All right, part B has combining kind of multiple functions, derivatives again. So again, take a minute, pause the video, click play to check your answer. In our next problem, we're going to look at utilizing the power rule to write the equation of a tangent line. Now, technically, this is something we already know how to do. Obviously, we're going through the power rule in this lesson here. And in the previous lesson, we looked at using derivatives to find equations of tangent lines. Here, we're just going to put those together and put some emphasis on it just because writing equation of tangent lines is something that's for sure going to show up a few times on the AP exam. Okay, so problem 4, part A, write an equation of a tangent line to the curve y equals x squared plus 2x at x equals 3. Okay, so we want a tangent line which will take on the form y minus y1 is equal to m times x minus x1. All right, our point slope form equation of a line. Okay, we can't jump straight to slope intercept form. I suppose technically we could, but we're not going to be sure what the y-intercept is right off the bat. Okay, so what we need to do here then is just fill in this m, x1, and y1. Our x1 is just the x value we're going to take the tangent line at, the 3. So we can fill in that right away. y1, that's going to be the y-coordinate when x is 3. So I can plug that x equals 3 into my equation. So it'll be a 3 squared plus 2 times 3. 9 plus 6 will give me a 15. And then from there, we just need to find the m. In other words, the slope of the tangent line at x equals 3. First thing we'll do is we'll find the equation for the derivative. We'll find y prime. Now, using our power rule, x squared is going to turn into a 2x to the 1, plus 2x will just turn into a 2, which means my m, my slope, will just be my derivative with 3 substituted in. So 2 times the 3 plus 2. In other words, an 8. All right, so there's an equation for my tangent line. Now, free response time, this works. That's the equation. We can stop there. But multiple choice time, usually what the options A, B, C, and D are going to do is have this equation in terms of y, solve for the y. Let's go ahead and do that quick. On the right side, I can distribute that 8 through, which will give me the y minus 15 is equal to 8x minus 24. And then add 15 on both sides to get the y by itself, which will give me y is equal to 8x minus a 9. Now, we don't need to use a calculator for this problem, obviously. We've got the answer. But in some cases, it's a good idea to pull the calculator out and just after the fact, take a look at what we found. So here I've got plugged in to graph the original equation, y equals x squared plus 2x, along with the equation for our tangent line, 8x minus 9. When I graph that, what I can see is my x squared plus 2x here. Okay, and then the equation of that tangent line looks like this is going to hit our graph at the x equals 3 there. Okay, so again, that's what we're looking to find is that tangent line, that line that intersects the graph at a single point. All right, part B is the same idea. Once again, take a minute, pause the video, work through that run, and then hit play to check your answer. Last thing we're going to do today is look at using tables of values of functions along with derivatives, or just values that were given to evaluate some derivatives. Okay, so problem 5 says the following table lists values of function f and g and their derivatives f prime and g prime for various values of x. So we've got x equals 1 and 3. And then we have the values of f and f prime along with g and g prime for those x values. And we want to use that to find, well, in part A, let h of x equal 2 times f of x minus g of x plus 3. We'll use that to find the derivative of h at 1. Okay, 2 steps for that. First step would be to find an expression for h prime, the derivative of h. Will be equal to, okay, 2 times f of x. Well, that'll just be 2 times the derivative of f. Okay, minus g of x, so minus the derivative of g of x. All right, and then that plus 3, the derivative of a constant is just nothing. Let's remind ourselves that's a plus 0 here. And then once I have that expression for the derivative of h, I can plug the 1 in. So this is going to be h prime of 1 will just be 2 times f prime of 1 minus g prime of 1. All right, so we can go to the first row of our table for that, which has x equal to 1, and get f prime of 1 and g prime of 1, and plug those in. So this will be a 2 times f prime of 1 is 5. Okay, minus g prime of 1, which is negative 2. So minus negative 2 plus 2, in other words, which will give us for a final value just a 12 here. All right, with part B, same idea. Take a minute, pause the video, press play, check your answer before you wrap things up for the day. All right, so that's it for lesson 2.2 on the power rule. Okay, hopefully you're recognizing that that makes life a lot easier than finding limits using, or finding derivatives using limits. Okay, so go ahead and get going on the homework with that. Utilize that every time you come across a function written in terms of power from here on out. And if you need help, like always, make sure you're asking. We'll be there to help you out. We'll see you next time.